Good morning. Today we are going to discuss about hidden Markov model. It is a very popular model for time series data. Let's first look at some of the applications of hidden Markov model or HMMs as they're known in short, and then we'll walk through the basics behind the model. One very important application where HMMs have really taken off is activity monitoring. So imagine that you have accelerometer data from your cell phone or from your Fitbit like device. Now, this is going to be changing as and when you're changing your activity. For example, the accelerometer pattern when you're walking would be different from the accelerometer pattern when you're running versus sitting. And let's say that we have a finite set of activities that we're trying to monitor, be it walking, running, sitting. Now, one thing to notice here is that this data, accelerometer data, is a time series data. So, could we use traditional conventional machine learning algorithms that we've been discussing thus far? Could we use logistic regression? Yes. But is there a benefit of using something which takes a sequence into consideration? So, that will be the discussion of this lecture. Another example where HMMs are very highly used is speech recognition. So imagine if you have a raw speech. This could be coming in from your smartphone where you're trying to talk to your Google Assistant or Siri or Amazon Echo, Amazon Dot, or Cortana. So given this raw speech, there would be some component which would transform this into features. These features could be MFCC features, other frequency transform features. And the machine learning task here is that you want to construct or you have to convert the speech, spoken speech, into text. This would be words like I like, machine learning. Of course, there's again an important sequential aspect of machine learning here. For example, if you've written I like, so you would like certain kinds of things, right? You will not like certain kinds of things. So there is a language model which could come into picture. Thus, knowing that the first word is like, first word is I, second word is like, the third word in this particular sentence will be affected by the language model. So again, there is some aspect of the sequential data coming into picture. There are many such applications such as part of speech tagging. For example, if you have a sentence, you want to be able to tag whether the words are adjectives, where are the verbs, where are the pronouns, nouns, etc. And there are a lot of applications in the bioinformatics space. Before we go into understanding much more about HMMs, let us try to look at some more types of sequential data. First, the amount of rainfall, the daily rainfall, could be an interesting kind of sequential data. The price of the stock is time series data or sequential data, words in a sentence. Now, you generally don't associate sentences with the notion of time, but you could very well associate them with the notion of a sequence. As I was discussing, if we go back and I've written here, I like machine learning. So after I've written I and like, given that this is a machine learning class, this might be very, obvious that you might want to have words like machine or they'll have higher probability. Now, if you've already got three words like I like machine, what is the probability that the fourth word is learning? I would say pretty high because let's say what could be the alternatives? I like machine drawing, I like machine parts, I like machine cleaning. Now, amongst those, learning seems to be probably more suitable. There could be other kinds of sequential data also, like the energy consumption of a home. So let's try to understand what distinguishes sequential data from the regular data. Let's take an concrete example of the weather. We'll say that there are only three kinds of outlooks. Either a day could be rainy, sunny, or cloudy. and we denote the observed outlook at the tth day by x underscore t, and we could thus come up with an observation sequence which looks something like the following. The first 3 days are rain, the second two are cloudy, the next two are rainy, so on and so forth. Now, if I were to tell you that it's been raining for the previous 10 days, what do you think would be the probability of raining today? I would imagine it being very high because if it's raining 10 days in a row, it would likely be the monsoon season in India, right? So in monsoon season, if it rains today, it very likely rains the next day also. So this brings us to an interesting standpoint. We had previously discussed that could we use regular machine learning methods which we've been studying thus far, let's say classification technique like logistic regression, to predict the activity that we are on based on accelerometer data or so on and so forth. We could do that, but if we're doing that, we're essentially treating the sequential data as IID. So we are totally ignoring the sequential aspect of the data and considering observations to be independent of each other. Could you pause for a moment, think for a moment, and figure out why ignoring the sequential aspect is not a very good idea? So the most important reason why this is not a very good idea is because it is failing to exploit the sequential patterns which exist in the data, which is to say that nearby observations are going to be correlated. This is going back to the example which I was giving just a few minutes back. If it is raining today, it is a very high probability event that it will rain tomorrow also, because there is an weather is going to largely exhibit some continued patterns of patterns where there is some correlation between adjacent observations. So this is where it makes sense to treat sequential data as indeed sequential and not treat it as IID observations. Now, the model that we are trying to study is called Hidden Markov Model or HMM. Let's try to break it down into different pieces. The first such piece is called a Markov model. I believe some of you would have already studied Markov model in some of the prior courses, like probability courses or some mathematics courses, or even some other applied statistics courses. So just consider this to be a refresher if you have already studied such a course. Now, what I've done here is I have marked t random variables x1 through x capital T, and I've also shaded them. So the shading is generally a convention used in graphical models to indicate that a variable is observed. So x underscore capital T is the observation at the th timestamp, and x1 through xt are the observations from x1 from time 1 to capital T. Now you might notice that there seems to be an arrow going from x1 to x2 and x2 to x3, so on and so forth. What do you think this means? Now we are talking about, in some sense, this is it's a very simple graphical model that we have presented. What do you think the arrow is indicating? So the arrow is telling about the relation between x1 and x2. That x2 depends on x1, x3 depends on x2, so on and so forth. Before going forward, let me introduce another technical term here. It's called the first order Markov chain. Now, the first order Markov chain is exactly what has been depicted at the top, where x2 is there is an edge from x1 to x2 and an edge from x2 to x3, so on and so forth. The technical definition of the first order Markov chain is that the future prediction is independent of the past given the present. So let me repeat again. The future is independent of the past given the present. This might seem a little confusing at first. So let's go a little slow and try to understand this with the help of some colors. So we want to say that the future prediction. So let's say that we are at time small t, right? So the future prediction, let's say, is we're considering only one time step ahead. The future prediction then is x underscore t plus 1, right? And I'm telling that it is independent of the past given the present. So we are currently at time small t, thus the present is x underscore or x subscript small t, and the past is the sequence of observations from x1 through x small t minus 1, right? So this is indicated in the orangish yellowish shade. So what the first order Markov chain assumption is stating is that the quantity on the left hand side is equal to the quantity on the right hand side, and the quantity on the right hand side is that the future prediction is dependent only on the present, and given the present it is independent of all of these terms on the left which denote the past, right? So if you were to calculate the joint probability of this entire chain or graphical model, how would you do that? Could you think for a minute, not look at the slide? So you want to basically uh, tell the joint probability of x1, x2, x3 till x capital T. Could you think for a minute and come up with a joint probability? I'm assuming you did this exercise, and let's go ahead and look at the joint probability. So joint probability of x1 through xt, if you notice for the first node x of 1, now this does not depend on any of the other terms in the sequence, right? So the joint probability is for the first term you just write probability of x1. Now just looking at the first order Markov chain assumption, the probability of x2 given x1 is just the probability of x2 given x1, but the probability of x3 given x1 and x2 is independent of x1. So probability of x3 given x2 comma x1 is just the probability of x3 given x2. So indirectly what you're trying to do is to just write out the expansion where each node is only dependent on its parents. Thus the joint probability would turn out to be an expression which looks like the following: probability of x1 times probability of x2 given x1 times the probability of x3 given x2, and you keep on multiplying such terms, and the final term would be probability of xt given xt minus 1, right? So having now discussed the first order Markov chain, could you think what a second order Markov chain could mean? Could you just think for a minute and just write down your answer, and then once we discuss you could compare it with the answer that I'm showing. Okay, assuming you have done the exercise, the graphical model for the second order Markov chain is shown at the top. If you notice, it is fairly similar to the first order Markov chain, but there seem to be some extra edges. Previously, if you notice that there was no edge from x1 through to x3 for the first order Markov chain, but now there is an edge from x1 to x3, an edge from x2 to x4, so on and so forth. So the second order Markov chain says that the probability of the prediction of the future given all of the past is independent of all of the past except for the previous two observations. So xt plus 1 depends on xt and xt minus 1. So if you look in this particular graphical model shown at the top, x3 has an edge going from x1 to x3 and from x2 to x3, right? So thus x3, the probability of x3 given all of the previous data is only dependent on x1 and x2. Could you again take a minute and write the joint probability for the second order Markov chain? So the interesting bit here would be that for the first order Markov chain, once we wrote the joint probability, there was a term x1 which was dependent only on, which was not dependent on anything, right? Whereas for the second order Markov chain, we have an x1 term which does not depend on any other term, but there is an x2 term which depends on only one term x1. All of the remaining terms from x3 till x capital T depend on two previous terms, right? So if we keep on going in this fashion, we'll end up with a joint probability which looks like the following. Probability of x1 times probability of x2 given x1 times the product of the following probabilities of the form xn given xn minus 1 and xn minus 2, where n is going to vary from 3 to capital T, right? So let's come back again to the first order Markov chain, which is going to be the focus of this entire lecture. The hidden Markov models that we are also going to be studying are also going to be based on the first order Markov chain. So we come back to the first order Markov chain and we saw that probability of xt plus 1 given all of the previous data is equal to the probability of xt plus 1 given the current observation xt, right? And we can thus also write the joint probability going forward in this fashion. Now let's try to understand that what are the parameters of the first order Markov chain, or in other terms, if we have to characterize the Markov chain or the Markov model, what all parameters do we need? Even before doing that, we need to very carefully note down the main assumption of stationarity, which is to say that while the data might evolve over time, but the distribution from which the data is generated is fixed. So the example of data evolving over time could be if we go back and we were discussing about some samples from the outlook of a day, right? So we'll of course have different kinds of observations. Sometimes you'll have a sequence of R's, C's, R's, S, C's, etc. The sequence, the sequence of observations might be variable, but the underlying process which has generated this data, or the distribution from which the data is generated, is said to be fixed. This is a very useful property, and this will sort of simplify our calculations and what we plan to do in the case of HMMs. The other way to look at this property is that we would want to have some parameter sharing, or we would like to have some parameters which are independent of time. So if we forget about this, if we do not consider the second assumption, then if we go back to this joint probability, then we'll need a lot of parameters to characterize any given Markov chain. We would need a parameter to characterize the probability of x1 or the first observation, probability of the second observation given the first, probability of the third observation given the second, and so on and so forth. And this is also going to be dependent on the length of the chain. So the key ideas could be come up with a parameter sharing concept where the parameters are independent of time, right? Which also means that we'll want that the probability of x of t given x of t minus 1 to be same across all of the t's. So which is to say that if it is the probability of, let's go back to this example of rainy and cloudy and sunny, right? So we have on the first day it is raining, on the second day it is raining. So the probability that it rains on day 2, given that it rained on day 1, we'll want that to be same as the probability it will rain on this particular day, given that it rained on the previous day. So this is all there is to what we just discussed, that the probability of xt given xt minus 1 is the same across all t, and which basically means that the parameters are shared and these are independent of the notion of time. Right? Now, knowing this, we could rewrite the joint probability in a much more succinct fashion, saying that the joint probability is probability of x of 1 times the product of the probabilities of the form xt given xt minus 1, where t is small t is varying from 2 through capital T, and this big pi symbol is indicating that there are successive multiplications. Right? So what do you think are the parameters now required to characterize this first order Markov model or Markov chain? Think for a minute. So the parameters needed to characterize this have to be coming from this joint probability itself. Now we notice that there are two types of terms. One, probability of xt given xt minus 1, and the other kind of term is probability of x1. So we have two parameters to characterize a first order Markov model, and we call the set of parameters as theta. It's a two element tuple containing prior probability pi and the transition matrix A. The I've also colored them accordingly to show that the prior probability pi corresponds to probability of x1, the probability of the first observation. And in the pink, I've shown the transition matrix, usually denoted by the letter A, which is incorporating probability of xt given xt minus 1. Now let's try to understand both of these terms, prior probability pi and the transition matrix A. First, let's look at the transition matrix A. Now, we're going to assume that x small t can take one of k states. For the case of the weather example or the outlook example, what is k? So the k was 3. It could either be cloudy, rainy, or sunny, right? Now we define the term A sub j k as the probability of x of t being k given x of t minus 1 is j. So here both j and k are could go from 1 through k, and these denote different states. For example, j could denote rainy and k small k could denote cloudy or sunny. So you could, or even rainy again. So j and k are both, j and small k are both a subset of 1, belong to 1 through capital K. Now what this is telling, the term A of j of k is indicating that there is a transition from j to k. Previously you were in state j, now you've moved to state k. So that's how it's typically written. A of j of k means the probability of transitioning from state j to state k. Now there could be many such ways in which the transition matrix could be represented. We'll be looking at three main ways in which the transition matrix could be represented. And this is very useful to develop good understanding into the model. The first such way is a tabular form. So we said that uh, x of t, each of x of t could be one of k states. But similarly, we could have each of x of t minus 1 to be one of k states. Thus, in this table, we are capturing the transition. If we look at the first row, it will be a1, 1, because it is telling us about transition from xt minus 1 equal to 1 to xt equal to 1. The second row is a transition from xt minus 1 equal to 2, the second state, to xt equal to 1. Thus, this entry is a sub 2, 1. And similarly, the final entry would be a capital K, capital K. Right? We could also look at the transition matrix or the transition matrix parameter in the form of a finite state machine. Let's say we have these different states. The probability that you go from state 1 to state 1 back is a1 to 1. Probability of going from state 1 to state 2 is a1 2. Similarly, going from state 2 to state 2 is a2 2. From a general state j to another state k is ajk. The third way in which this could be represented is via an adjacency matrix. Now, this is a matrix with capital K rows and capital K columns, where you're denoting a transition from x of t minus 1 to x of t. The only thing you need to be very careful about in this is ajk means the jth row, the kth column, which means that you're transitioning from xt minus 1 equal to j to xt equal to k. And this is the usual form which we also use while writing the code for HMMs. It's very natural to think of it in this way. Now let's try to look at the next parameter, which is the prior probability pi. Now we said that there are k states, capital K states. So we denote the prior probability pi of k, where k is from 1 through capital K, to be the probability that the first observation is, or for the first time instance, you are in the kth state. Right? So this is basically the probability of the first observation. To make our understanding more concrete, let's look at an example. It's using the basic weather or outlook example that we had discussed earlier or mentioned earlier. So we have described the variable pi. It's going to contain 3 columns and 1 row. This is on the basis of the fact that there are capital K equal to 3 states. The first column represents the probability that the first observation, or at t equal to 1, once you start observing, it will be a rainy day. The second column tells the first observation on day t equal to 1 would be a cloudy day, and the third one tells us it would be a sunny day. And similarly, we have a transition matrix, capital A, which denotes the probability of going from a state, jth state, to the kth state, right? So the first question for you at this point of time is, could you tell us what is the probability of the sequence rainy, rainy, sunny, sunny, cloudy? So think about this question for a minute. Try to work it out in your notebooks. Okay, I'm assuming you pause the video, you try to work through the example. The main things to look at here is, firstly, you're trying to model the probability of the set of observations given the model parameters theta equal to a and pi. Now, all we need to do is to just write down this joint probability of x1 through x. What do we have? 1, 2, 3, 4, 5 observations. and just break it down as we had done in the most general case. So the first term is probability of x1 equal to r. Where do you get this term from? You'll get this from the prior probability. That so pi of r shown in gray, tells us that the probability of the first observation being a rainy day. The second term is probability of x2 equal to r. So we need to look in this particular set of observations. The first observation is r. The second observation is also r. What is the probability of such a transition? So that transition is given by transition A of r to r, which if we look at in the transition matrix A is the first row and the first column. The next term in the joint probability would be a transition from R to S. The next would be a transition from S to S, and the final would be a transition from S to 3. So the transition from R to S is shown here in this light pink shade. The transition from S to S is shown in this red highlight, and then finally from S to C is shown in this greenish shade. Thus, we have now written the joint probability of this sequence based on the terms which exist in the transition matrix and the prior probability, or pi. Okay, so a similar question to this is, given that the first observation is given that the probability of the first observation being rainy is 0.2, what is the probability that the second observation is r? So as such, you don't even need to think about this explicitly, given that probability of x1 equal to r is encoded in the prior probability matrix and to the prior probability vector. Could you work this out? Pause the video for a minute and work this out on your own. Okay, assuming that you have worked this out on your own. Now, you want the probability of x2, calculate the probability of x2 equal to r. Now, you could observe x2 equal to r based on x1 being r, and then making a transition from r to r, or you could observe x2 equal to r starting from state S and then making a transition from S to R, or you could start from the state C and make a transition from state C to state R. So which, if you complete the calculation, will come out to be 0.2, which is interestingly the same number as the probability of the first observation being rainy. As an additional exercise, I would like you to work this out for the other variables also. So what is the probability of x2 equal to C, probability of x2 equal to S? Do you get the same set of values? If yes, then why could this be the case? Right? Okay, good. So we have thus far understood first order Markov chain, but now let us try to understand hidden Markov model. The first question that you might want to answer is that what is this hidden term, right? What is the hidden component? To understand this better, we'll look at a sample application. We'll call this the coin toss model. We'll say that we have two types of coins. One is a biased coin, where the probability of heads is 0.7 and the probability of tail is 0.3. And then there is an unbiased or fair coin, where the probability of head, as you would expect, is 0.5. Now we can see only the sequence of observations, which is given by x, which could be head, tails, etc. The hidden component comes into picture in the following sense. We do not know which coin was tossed, right? So this might be one of the questions which we are trying to predict using our machine learning framework. Which coin was tossed at what point of time. Now, let's try to relate the HMM with the Markov model, what we have studied thus far. So we can very easily see that there are two coins now. Let's apply a Markov model on those two coins, or these can be basically different states your system is in, right? Your system could be either in a bias state at any particular point of time or in a phase state. Now, given these two states your system could be in, there will be an associated probability of remaining from the bias state and in the next timestamp also remaining in the bias state, or going from biased to fair, going from fair to biased, or going from fair to fair, right? Which is pretty much what we have seen thus far in the Markov model. And the new component that we'll now see is there is something known as an emission, right? So we've said that the bias coin has a much more likely to produce heads compared to tails, whereas the fair coin will emit out a similar amount or similar likelihood of seeing a heads and a tails, right? To make the discussion more concrete, we look at the graphical model for HMMs. We'll first look at the Z values. So Z here are indicating the hidden state or the state in which the system is in. It could be either coin 1, coin 2, or to keep it in, to say it another way, if the system is at time Z t, is it in a bias state or is it in a phase state? And we say that these two different states and the sequence of states is following the Markov model in the first order Markov chain, right? But then there is a sequence of observations that we are also observing. So corresponding to your state at time 1, which is Z1, there will be an observation at X1 that you'll see. It will be either a head or a tail. Similarly, you'll see for each of the T or the capital N set of observations what the state could be. So just to summarize, Xi here talks about the observed state, and as you would expect with observed states being shown in gray or highlighted, and the Zi is indicating the latent state, right? So an important thing to note here is that the observations do not follow the Markov chain. So there is no link between x1, direct link between x1 and x2, right? But there is a direct link between z1 and z2, right? So given this background, could you think about what are the parameters which would characterize a hidden Markov model? One of the important hints is that the only new component that we have added to the hidden Markov model over and above the first order Markov chain is an emission. So going from Z, so the probability of observing X1 equal to head or tail based on what is the state, hidden state Z1, right? So assuming you had some time, you pause the video and stop for some time and thought about the HMM parameters. The three HMM parameters are first, the transition matrix A, which is fairly similar, or exactly the same as what we'd seen before. AJK indicates the probability of going from state J to state K in successive states, right? In successive time steps. The only thing you want to very carefully note here is we're talking now in terms of Z variable and not in terms of the X variable, because it's the Z variable, the hidden state variable, which is following the first order Markov chain. The second parameter is the prior probability pi, where pi of k tells us the probability of starting in state k. So basically probability of Z1 being k. And the third parameter is known as the emission probability, usually denoted by the symbol phi. So for this, we need to define the distribution of the conditional of probability of x of t or x of n given z of n and phi, right? Now, there could be multiple ways in which you could define this probability distribution. We'll look at two simple cases. First, when phi is discrete. Now, this is similar to the model that we've been discussing thus far, where Zi is the state of the system or the coins. It is either fair or biased. And phi is now telling us if Zi equal to fair or biased, what is the probability of observing heads or tails. Right? So for us, we could define phi in terms of a conditional probability. Phi of f or the fair state would be 0.5 and 0.5, whereas phi of biased would be 0.7 and 0.3, assuming you first put heads and then put tails. Right? As a second example of how you could define phi, let's assume that trying to model the energy consumption of an appliance. Right? The state of an appliance could be, let's say, only binary states. Either an appliance is on or off. And the observation that you have for each time instance is the amount of power being drawn from the appliance. Right? Now, you could pretty much imagine that if the appliance is off, it would be consuming zero power, or close to zero power, assuming that there is some observation noise. And when it is on, it would consume, let's assume a very simple appliance model, it will consume an roughly same amount of power. So we could pretty much model that phi for the state on is given by power to be normally distributed to the mean 100 and variance 10. And being off, power would be given as normal distributed with mean 0 and 5. Of course, there are other technical aspects to it which I'm not currently looking at. For example, you would want it to be power to be strictly non-negative. But we have thus far assumed that there is some noise, observation noise. So at this point, let's get back to the application of activity monitoring and try to understand that what could be Z's and Xi's. That would give us a better understanding of how to use HMMs in the real world. So we've seen this activity monitoring application, and we said that there's some accelerometer data that you obtain. Now, the activities that you are in would be the different states. So it could be, let's say, Z of I could be a state, could be a subset of walking, running, one of walking, running, or sitting, each of Z of I. And based on the state you are in, you would be emitting. There would be an emission factor associated with it. Based on walking, there'll be some different kind of features you will be producing, with different kinds of XIs. Now, these XIs could be some transformation of the raw data. How we do the transformation or what kind of features do we use, I'm not going to tell currently, but that is something you should be thinking about. Let's pause for a minute before we look at the different kinds of problems we solve in HMMs.